Hello and welcome to 18th lecture of the course on data-enabled tribological engineering from experiments to predict models. The topic of this lecture is measurement and analysis of wear debris. So let me start with the definition of the wear debris, which I understand. We say wear debris means small particles which is coming out from surface because of the surface deterioration of material. The aim of this course is to minimize the surface deterioration or surface degradation. So naturally, if particle is coming out of that and if we can examine, if we can analyze, then it will be much more beneficial. Reason being, many times to find out the failure, we need to open a complete system. But this wear debris can be completely removed from a surface or interface by using the lubricant. So this is where we come up with a wear debris analysis. Now what we are showing in this slide, some picture of the surface which is getting degraded. You can see there are a number of debris particles which are still attached to the surface. They have not been separated, but are about to leave this surface. And then when the particle comes out, they may come out something like this, slightly complicated shape of the debris, some spherical shape kind of debris, some glowing particle, and some plate shaped debris. So there are different kind of the shapes which we can get. And we are saying lubricant, if it is processed or it is passing through interface and it's coming out and getting recirculated, then these debris particles should be filtered out. Reason being to avoid the three body abrasion. And three body abrasion we have studied in lecture 4. That it will cause a wear, of course, as not that bad as a two body abrasion, but it will cause a wear. So if particles are getting removed and again lubricant is coming there and providing the gliding surface and low friction and low wear rate, that will be the beneficial to us. So what we can say here, the analysis of wear debris is required to assess state of component degradation. It provides a valuable insight into the health of mechanical system. The way human beings have been tested, like the we do a blood sample test and figure out whether hemoglobin is lesser or maybe the red blood cells are lesser. So we try to find out health of human being. Similar way, this debris analysis helps to provide a health of mechanical system. Now, what are the different kind of the particles? We say there may be different types which we have been showing here, even the different size. Few particle may be 1 micron size, maybe 10 micron size, maybe 50 micron size. And next comes what is the quantity which is coming per minute or per second. The quantity is on the higher side, naturally the degradation is on the higher side. So this gives a good information about the health of system or components. So that's why we give a lot of emphasis on wear debris analysis. What we say here again, the various forms of wear debris include adhesive wear. Naturally, what if the debris comes out of the adhesive wear will be slightly different than abrasive wear, and whatever comes out from adhesive and abrasive wear, that will be different from a wear debris which is coming out from a fatigue wear. Of course, corrosive wear will be having some sort of a chemical or maybe some sort of oxide layers on the surface, and we know that that can be done as an analysis also. It's not only the size, the type and quantity, but we need to see the chemical composition. That's why the spectroscopy needs to be brought into the picture. In my previous lecture, I say when we are thinking about the microscopic, it can be a SEM image also, a TM image also, but also spectroscopy. And as I give an example, FTIR we have done extensively, particularly to figure out what is happening to the oil. Many times because of the particles which are coming out of the surface and getting deoxidized, or it may be creating some sort of a different effect, particularly for lubricant. Maybe lubricant is reacted to that, which particularly the nascent surface or virgin surface. So that indicates that indication comes from a spectroscopy or FTIR. So we do extensively those analysis. Here we have say it can give indication of adhesive wear, abrasive wear, fatigue wear, corrosive wear. If we know what is the fundamental reason of the failure, we can do right corrective action, and each wear type will have unique properties, and that's where the wear debris analysis comes in a bigger way. And also we say that we need to examine those properties so that timely intervention can be made to avoid the breakdown of equipment and prolong the durability of the machinery. Here again we are using the word, we are going from macro analysis to micro analysis when we are talking about the wear debris analysis, because mostly wear debris will be at the micron level, and we are trying to analyze, and instead of the whole surface gets damaged, we are able to figure out initially there is some chances of failure, there is some faults has started initiated, and we should do a corrective action to correct there. Maybe if there's a misalignment, or if the oil choice is bad, or maybe oil additive have degraded, something like that, so we can change the oil also. So those correction can be made, or those corrective action can be implemented if we know this kind of information. The same thing like we check our temperature, body temperature using thermometer, and we know that if there is the temperature or maybe the fever, we can take a medicine. Same thing happen with equipment also. So whatever we are able to figure out, yeah, if there is a chances of adhesive wear, we will do correction according to that. If there is chances of abrasive wear and maybe the three body abrasion, then we need to check whether the filter is correct now, or maybe we need to replace a filter. Or if the fatigue wear is happening and that's a low cycle fatigue, it does not sustain the life, naturally we need to see what is really wrong with our load situation, speed situation, or maybe the alignment situation. If there is a corrosive wear, we understand, or maybe there's a possibility the moisture content has increased in the oil, and then there's a need to change it, or tan number has changed different manner, TBN number has reduced, so we can change those things. So whenever we get this kind of information, we can do corrective action, and that too at particular time, that time itself, so that we can avoid the breakdown of the machine and then prolong the serviceability or durability of the machinery. I'm just showing a previous figure. In lecture 17 we showed scoring of the gear, and then we showed a mark and a zoom of the this one 200x we have shown. Similarly scratches we have shown over here. Now question comes, if instead of going to this stage of the gear failure, because gear teeth cannot be taken away from the gears without cutting it, without damaging it. So if we are able to figure out that gear is about to fail or is moving on the path of the failure by collecting the debris, so these are the debris which can be collected, and this gear failure can be avoided. So if you are getting a particles and we say, oh, maybe it's an abrasive particle, maybe adhesive particle, so I can use a word here, this is adhesive particle, and that means the lubricant is not playing important role, or this is abrasive particle, maybe the load has gone up, or maybe there is some sort of particle, or maybe some clearance, or maybe say some sort of misalignment which is happening, and then it is increasing the abrasive particles. So we can take a remedial action well in advance. Now question comes to what was happening earlier and then why we are talking about this. Yeah, most of the industry, they do use spectrometers to find out the quality of the oil, because mostly they know that oil they utilize some sort of additives, and being these additives will be utilized with a time, and then maybe say after 1 year time EP additives will be getting exhausted and DVR additives will be getting completely utilized, so we need to change the oil. So that purpose spectrometric analysis is good, and then only problem with the spectrometric analysis is that any particle size more than 10 micron size is generally rejected, and where debris start from there. You say no, don't reject 10 micron size particle or above than that. Those particles are very important to figure out whether the surface degradation is on the high side. Of course, now when we talk about the wear debris analysis, this is slightly costlier, and it requires more algorithms and more time consuming compared to the magnetic plug, which is very simple, and then We know that when the magnetic flux has some sort of 100 micron or 1000 micron particle size, it will have some sort of signal, or maybe if it is going beyond that size, it will stop the operation. It can trigger the motor button, and this, the machine should be stopped. So here what we are saying, that disregarding particles larger than 10 micron, which is a very important, particularly from tribological point of view. It's a major shortcoming of spectrometric analysis which was done earlier, particularly what they used to call as a SOAP analysis. And we are picking up this pictures and directly from tribology handbook, which was published in 2001, digital version, and a PDF file is available online. If you want, you can download, and this complete information is available there. Now here what we are saying, what is the way ahead? This information has been already given and published. What is a really next thing is a data from where debris analysis. Now we can utilize, because we know that there are number of sensor which has come up, and we can go for online analysis, we call as a wear debris analysis. Or maybe we can make some sort of sensor and IoT based sensor which can give the information to us. So we collect those necessary information, and then if it is possible to develop a system which can really reproduce the same system again. Like if there is a fresh gear and then somewhere debris are coming out of that, and if I am able to collect the information related to where debris, particle size, and location from which place those where debris are coming out, so we can rebuild it. That means whatever the software which initially we made, and we did a gear design, and after that the gear was manufactured, assembled, and installed. Now here we are getting reverse information from a gear setup, that this many wear particle have come out, this much wear out has already happened to the surface, and we rebuild that. We do modification in our own software, whatever the we did a modeling of the gear, implement those things, and then again check a performance. And that's what we use a word, cyber physical system. There's a physical system, and here the information is coming from physical system to our computer network, and then we are building a system again, and we are saying this is a now twin, or the way we use a word, a digital twin, the way we keep a mirror and we see our face, our replica comes in a mirror itself. The same thing in this case, if we are getting IoT device and we are getting signals, we can make a cyber physical system, and we can really see what is happening into the complex system inside, or sitting on our computer itself, and then doing a complete analysis, and we realizing initially the gear contact ratio was 1.6. Now because of this wear out, contact ratio has reduced to 1.5, which will increase the load. Naturally there is something to need to be changed in case, or we know that you are well in advance that now contact ratio is 1.5. After 100 hours or 1000 hour, contact ratio will turn out to be 1.2, and we need to replace this gap. So we can plan everything in well in advance. So this is what we call a real time insight into the state of physical asset. We keep getting information from a physical system, and those informations are rebuilt, reconstructed in a software, and then based on that we really figure out what are the remedial action. So we can predict failures well in advance. Again, I'm using the word, in future we will not go for failure at all. We will figure out what kind of faults are getting developed, can we correct those faults immediately. If it is, the failures will not occur, and sustainability will be met. As I say, that resources are getting completely eliminated, and then we don't have to rebuild the system. Same system can run for the years and years. So that is very important. It also gives us some sort of help assistance in the maintenance, and then if we know that system cannot be rectified, and after 1000 hours we need to replace, so we can order that component and we can replace well in maybe say when the time to go to failure we are indicated or we are predicting. So everything can be systematic, and breakdown will not happen. Every time everything will be scheduled, and because of that manufacturing will not be lost, efficiency will not be lost, and then even the deterioration of the surfaces can be delayed as much as possible. So these things will be a more beneficial. So where in the I believe that where debris is really going to give a lot of information, and that will helpful to build the cyber physical system, and that will be really useful to delay the degradation. As in beginning of the course I said that wear cannot be eliminated, but it can be delayed. So instead of the operation 10 hours, we can make it 100 hours. Instead of 1000 hours, we can make it 10,000 hours. Those things are possible because we will be knowing in real time what is happening, real time what are the flaws. Earlier we used to model based on some assumption and implement, and maybe 90% equipment were successful. We used to feel happy, oh, reliability is a 90%. But now in these days we don't want 90%, we want 99.99%. We don't want to go ahead with any failure, because we know the failure means lack of the science or lack of engineering. An engineering domain, we don't want any kind of the failure. Now, one more important thing in last lecture I mentioned dry versus lubricated case. I showed also the one table, and we show that um, between two labs variation in results can be as high as 48%, which I will show the ratio of the standard deviation to mean. Now naturally the everywhere the lubricant cannot be utilized. Few systems work without lubricant also. So we need to think about what kind of wear debris will be coming out of that. So that's why the first question is starting with the dry wear. We say metallic wear may be unavoidable when oil, grease or solid lubrication which are not we don't have a possibility to implement there. However, one good point comes by nature is the oxide formation. So oxide layer will be acting as a lubricant. That's what has been written here. Oxide layer provides a lubrication. Even though I say is a dry, but there is already oxide layer on a surface. If you take any shaft, any steel surface, any aluminum surface, there will be some oxide layer on the surface that provides initial lubrication. So this is where we say that the oxide layer is a helpful. Now if the operating temperature goes on a high side, high hotspot temperature at the aspirity, or maybe high speed or high load, at the high temperature again this kind of oxide layer will form, and that is a very important aspect. We say creation and oxidation of fine wear particles which can cause a red color in extreme circumstances. So in those oxide layers there will be some sort of lubrication, so we will not get a major failures. We may again get a fine wear particles, and if you examine those wear particles you will find oxide layer, or sometimes a discoloration or change in color, like aluminum may become a black and iron may become a red, something like that. So there is a possibility. So this is what we are saying, creation and oxidation of the fine particles, or maybe there is already oxide form, and again if it is removed, again the particle also getting oxidized, then again we will find a difference in color. And we are showing the one picture here. You are able to see the some sort of wear out of the bearing, and this is the ribbon shape, and that is the same thing is written here. Severe catastrophic general machining or general the bearing failure has happened, and by a black scrap that develop in a bearing white metal lining, and then wear debris which looks resemble like a wire wool, right. So this is what we are saying, and that it kind of the chip formation, kind of the ribbon formation, kind of the curl formation happens. That's a special for the dry lubrication. Again these pictures have been picked up from tribology handbook, and then they have given also some interesting examples. We are saying that relative wear rate initially is on a higher side. As the operating temperature or surface temperature increases uh, from 100 to 200 to 300 to 400 degree, you can see here the wear rate is coming down. Reason being, at the low temperature oxide formation doesn't happen, but at a higher temperature and the intensity and then the energy level is a higher side, oxide formation occurs, and then we are able to see where our rate is coming down in this case. There is another example has been given in the book. They say that initially the low load there is a mild wear. At high load the rupture of the oxide layer happens. But beyond that load again, because of the operating temperature is going to increase, again oxide layer formation occurs. So there is a mild wear, there is a mild wear, and in between severe wear. So these are the typical examples, and then that's why the tribology has become very difficult to understand. So unless we understand mechanics properly, behavior of material will change significantly. We are not able to see a uniform behavior, monotonic behavior. Here everything is related to energy or entropy kind of thing, and then we require really chemical action when one action will be more dominating compared to other action. So that's why the data driven approach is very essential. It is not a material, it's a basically concepts or maybe say data or energy level data or say chemical reaction based data. They are playing more important role compared to just a component. Earlier people used to think, oh, tribology means only two materials. No, here the system is behaving different manner. It's not only the material science, it's not only mechanical engineering, it's not only the say that data engineering or computer engineering. This is a kind of all domain together, and that's why the it is more complicated, and of course we want to make little more complicated by bringing the machine learning, because we understand incorporating too many parameters without machine learning will be more difficult. To figure out what will be the sensitivity of those parameters will be very difficult. So that's why we bring initially all the concept, and then formulate or maybe say utilize a machine learning algorithm in a manner so we can make appropriate model for the future purpose. Now I'm showing one of the example which we did in our lab also. You can see here there is a graphite flax, and then carbon gets oxidized, and then when we are examining the wear debris, we find some percentage of oxygen, some percentage of carbon also in that. So this chemical composition of the wear debris and presence of lubricant also, it is really absorbing oxygen. So here the what we use a spectroscopic analysis is very essential. So when we do the spectroscopic analysis, we are able to figure out what are the chemical components of the wear debris, and this is very important to really find out, yeah, how do we utilize this in appropriate manner. Now coming to the little more detail, initially we have given some sort of glimpse of the dry lubrication, and if still we felt that dry lubrication still is not a dry lubrication, reason being there is some oxide layer on that. At a low temperature or a high temperature in the oxide layer, or maybe a lower load and higher load, there are oxide layers. So they act like a lubricant. Now coming to the wear debris analysis, we say we can divide the wear debris analysis in three domain. Of course, mainly two. Mainly two is a real-time monitoring, or what we call online monitoring, and offline monitoring. Of course, when we say online monitoring, again we do have two methods, what we call inline monitoring and online monitoring. What is the difference between these two? Is inline monitoring, we observe the primary oil flow within a machine. We don't bypass, we don't use any extra pump, we don't use any extra circuit, we just observe the lubricant, and for that purpose we use some sort of the setups, like what we say the magnetic system capturing the ferromagnetic materials, like a magnetic plug we earlier mentioned. Then we can also use inductive sensors which can really capture the material which is passing and then measure the how many materials have passed, or we can use some sort of filter to find out how much pressure drop is happening because of the copy and this particle accumulation. So based on this way, these all are indirect method, we really require some sort of simulation and then comparison calibration to come up with the right quantity or right value. Again there will be some sort of sensitivity or some sort of errors in that. However, second method is a online monitoring. Here we use a bypass section of the from a main oil. We have a small tubing and pump. We made a separate circuit, and then we can play with that. We provide a more and more sensor, and the oil which we are extracting only some percentage, maybe 1 to 2%, something like that. So focus on the bypass section of the main flow. And what are the method which we can include? We can include turbidity measurement. That's what we call in this case. But similarly, pressure drop we can also use the way we have mentioned in the filter system earlier. This is a major change where we can include wear debris sensor. This is important. Again, this detecting metallic particle through grid line kind of filter is a similar kind of thing, which will change, will record the resistance and change. But here we give more emphasis on wear debris sensor, which really account number of particles, size of the particle. It gives a different bins, lesser than 20 micron, lesser than 40 micron, more than 60 micron, less more than 100 micron. So they have a separate bins, 4 5 bins, and then they dump the particle and then give the particle, yeah, 40 to 60 micron is around 1000 particles, which the sensors are not really directly giving those kind of results. Now what is the future in that? Also we say the online wear debris analysis need to be made as a technology. What we really require, we required image processing, advanced image processing, and another one 3D reconstruction of assess equipment condition. So if I made a gear, as I mentioned in previous slide, that if we make a gear and as a model, maybe we are using solid model or inventor software or any three-dimensional software, and then if we are able to figure out using wear debris analysis or how many particles have come out, or maybe say image analysis, what is exactly shape of the particle and what is xyz coordinate in a different location, we reconstruct the complete system. That's also possible, so we can do that. Now this is the future, as I say that the advanced image processing and 3D reconstruction of assessing equipment condition over time, which can really predict the malfunction, and then which I'm just saying even the malfunction has not yet arrived and not has started, but we can predict those things also. And then it can enable the the proactive maintenance well in advance. However, still that is challenge. And what is this challenge? We say establishing a relation between wear debris, image analysis, and removal of the particle from a surface. So one is a debris, we are taking image, and then there is some removal of the particle from a surface, we are taking image, and then again bringing that debris on the surface. So that's a challenge. Still we don't have a complete technology, and that's why we say this technology is really required in the future to get a good results, or maybe say reliable results on that. Coming to the offline monitoring is well established. It has been in use for the years and years, and we have also extensively used. What do we do in that? We extract the oil sample regularly. It can be once in a 7 days, once in a 1 month, or once in a day, depending on the requirement, and we do analysis of that. What are the techniques which we use? We use a spectrometric analysis of wear debris. We use this ferrography or the magnetic gradient separation, what we have written. We use basically ferrography, and we have some sort of separation between the high particle size and low particle size. And then finally we are using also the SCM, that's what we have written, the microscopic examination of wear mechanism identification. Investigation, what do we do? When we say regularly, we collect the sample, analyze the debris, spectroscopy, elemental analysis, and we do a categorization of the wear debris. That's the way we have mentioned earlier, that wear debris sensor gives a categorization in a particle bin or maybe based on size. However, not only size, we can also think about the morphology or maybe the shape into the picture, and that will turn out to be very useful. Reason being, it will help us to understand the machinery condition, and we can suggest overall effective maintenance. So effective maintenance decision can be made based on this. So this will turn out to be very useful for the researchers or science student who are really attending this course. One more thing which is been mentioned, that as failure zone approaches, as the system is about to fail, number of particles will increase in number. So one possibility, and this figure was already shown in spectroscopy, ferrography, magnetic, maybe say where debris analysis we use here, and here we are writing instead of on that ferrography as a offline tool. Now at the beginning, initially we will find this kind of curve. You can see this is the 10 micron on the curve. Up to this we can say this is the 10 micron. This is a normal. Now failure onset, that means if we are getting this behavior, that means there is a chance of the start of the failure. And then we see the trend analysis, the failure will continuously increase. So this is where we can really continuously monitor if the number of particles are increasing or size of the particle is increasing. We need to really see, and in this case we are able to see both debris particle size is also increasing and then debris generation rate is also increasing. Both are increasing, and then we need to really see carefully. And of course this figure I have picked up from a literature. So in this case particularly, what says if particle size is greater than 10 micrometer, we require a detailed analysis, little more rigorous analysis to find out what is really happening. Is it happening because of addition, because of abrasion, because of the fatigue, and we really correct those actions whichever if there is something is happening that manner. If particle sizes are smaller than 10 micron, and mostly that we say it is initial wear or running in wear behavior, and maybe running in period is still continuing, that's why we are getting lesser than 10 micron size. But question comes, how do I really come up with a size? Who defines a 10 micrometer? As in my previous lecture, as I mentioned also, the sizes are continuously decreasing. Maybe earlier 10 micron meter was meaningful, but is it really? When we are downsizing, we are continuously decreasing the size of the equipment itself. 10 micron should be reduced to 5 micron, should be reduced to 2 micron. So this question will keep coming. And another thing comes, a trend analysis. We initially use and in lecture 3 we use a bathtub curve, and this was a trend 1. But we have also observed that it is not only this kind of trend, but trend can also be like that. If the surface, initial surface roughness, what we have been giving a lot of emphasis, that is very good, surface is extra smooth, then quite possible it is start directly failure, maybe it will not decrease. So initial zone, then this zone is completely missing, initial zone is completely missing in this case. That's the second trend. Third trend is that maybe we never reach to the quantity or maybe stationary level. You can see here that the quantity is not a rate, the quantity continuously increases. It's not the remaining constant at the one level. So it is started and it's a fail in this manner. So this is another trend. How do we follow this trend? How do I go with the trend 2, trend 3? I always feel, oh, trend 1 means if the initial level is where it is happening, it will finally come down to the significantly low level, and then we will go ahead with the steady rate. But in this case, it's not happening, it is not decreasing at all, and then it is continuously moving the straight line, and finally it is raising. So this trend is quite different. So whatever we are writing 10 micron or this, and I believe that these are the subjective thing, and we really require little more rigorous analysis. Like in this case, continuously increasing, it is not decreasing at all. And one more thing in this case is that it initially increases, so it's showing a kind of catastrophic possibility, but after that suddenly it becomes stationary. And so this is another behavior. So this is what we say, that initially the failure was nowhere, and they started again a very smooth surface we started, maybe the lubricant was not sufficient, and then and after that both the surfaces get aligned. Maybe initially there was some misalignment, some wear out occurs, and then they get aligned with each other after wearing out, and then after that is a failure. I mean, this is a stationary line or maybe steady line is continuously moving this direction. So there's another one, we can get a trend 5 like this also, and last one is a trend 6 in this manner. So we still in this case we are waiting, oh, it will go up, it will go up, whenever it will go up then only we'll have alarm. No, unnecessary, this is also one failure. So in overall, if we come up with a weird debris and then continuously check it, at least these trends can be avoided, and we following some trend or it will occur in this manner may not be necessary. Reason being, when where the weird debris is coming out, naturally we are losing some dimension. And initially, suppose I kept a 50 micron as a clearance between the two surfaces. If where debris is coming and 50 has become to 60 micron, I'm sure the vibration level will increase, load carrying capacity will come down, and then this failure may also be possible. So maybe say for a few hours, maybe a few hundred hours, performance was steady, but after the sudden failure occurred, there is a possibility. So that's why we say that this quantity need to be made in two ways. One is a size and particle volume. If size is here we are saying the debris generation rate, and this is a particle size, so both are important. So size is important, number of particles are important. So we need to account whenever we are referring any figure, we need to refer both. What is the really overall variation in coming that? And last one is a number of particles. What is really the number of particles in this? One more thing comes when we are talking about the 10 micron. Instead of that, why not we give as a percentage? If I kept a 50 micron as a clearance or interference, what is the percentage which is justifiable? See, okay, 0.1% up to 0.1%, we don't have to worry. After that, it is really going from ultra mild wear to the severe wear or mild wear. We need to think from that. A special case comes to the phatic wear, where there is an interference fit or transition fit, and we find that even the nut and bolt connection, they don't show any wear out from outside, but because of the micron level vibration, particles get loosened from a surface, and those particles start pitting the surface itself. So first the particle come from a surface, get hardened to some extent, and then again start digging into the material, parent material. So when we open up the nut and bolt connection or any rivet joint or any the interference joint, we find a lot of debris particles are coming out, and we find a big patch inside. So that has already worn out the complete system, and we need to replace. For small system, it will not be that difficult because the cost of replacement may not be that significant. Particularly for big system, wherever we have this kind of interference fit and all, we need to go ahead with a non-destructive testing, and we should examine continuously. So this is very important, and then we may not get a wire debris particle immediately in a visual form, but if in direct form, if we are able to get where particles are coming out, that will be really useful for us. So now that's why we say instead of going for one or two, why not we think about complete the domain of physical and chemical factors. So what are the physical factors? So we say debris concentration is one, morphology, color, and then chemical form of the debris also. As I say, the oxide formation occurs, then we are really looking into the chemical form. And debris can be any, it kind of like cutting wear can be like this also, and particle size can be bigger. Maybe say we need to see what is the really the aspect ratio or dimension in three direction, we need to really examine. So much more rigorous analysis of the debris are really required. So here we are talking first the particle counting numbers and size distribution, and then if we have a polymer material, then we use some sort of polarized light. If we have ferromagnetic material, we can go ahead with the ferrography. This is particularly the post analysis. And this here we are writing also something like because of it has been picked up from literature. In one case it is says, oh, sliding wear start whenever there is a more than 20 micron size particle. As I again may mention, these are the some relative size. Maybe for the one equipment was subsystem, not for everything. So these are just guidelines, and whenever we start working on some a machine, we need to really identify this particle size, particle range there. And another morphology, we need to see the shape, we need to see the physical characteristic of their particle. If there is a irregularity, we need to figure out. If there is some sort of a flat shape, a spherical shape, that need to be identified. And as I mentioned, the major dimension to the minor dimension or thickness ratio, Often it varies from 4 to 1 to 10 to 1. Naturally, when it's starting from 4 to 1, it may not be alarming significantly, but when it reaches to 10 to 1, literally it will be turning out to be very significant, and we need to see very clearly, yeah, is this a cutting wear? And then if it is happening, that means a severe abrasion is happening, particles are coming out. Quite possible, if we analyze this and we don't find any oxide layer in that surface or oxide component in that, that means there is a metallic wear coming out. If the metallic debris completely coming out, actually it is a severe wear form. It's not a mild wear form. However, if the particle is coming with a lot of oxygen or a lot of other additives instead of the parent material, main material, then it will not be worrisome. So we need to see the chemical composition, and that's why we are saying the chemical form is also very important. So we should see the wear debris in totality in a complete package kind of thing. So what we say that generated debris, if they are getting oxidized or chemical composition comes and we indicate get something like there is a sulfur, there is a chloride or oxygen, then we will not put it in a severe domain. We say it may be the mild wear kind of thing. And then we also see the color. Sometime we find the red color is coming out, that means there is iron particle or steel particles are coming out. Sometime we find a black color, we say, oh, aluminum or alloy is coming out. So we need to know what are the components inside a machine which are made of aluminum, and which aluminum part is really getting affected. And then if we can really combine the digital twin, or we say that the our system where the debris can be re-embedded, will be utilized to reconstruct the component, then that will turn out to be the best solution. Or we say, if you are able to make a cyber physical system out of that, that will be the very good indication to predict the wear well in advance, or predict the value well in advance. Now there are some sort of the indication as I given. Already I mentioned about the future. You can see here that we are finding out the some sort of wear debris. So this is a worn out surface, and this is a wear debris, and we are trying to assemble wear debris back into the shape from where it is coming out. So you are able to see wear debris here, and you are able to see wear debris here. So we are able to embed back in a system. So this is very important. Now coming to spalling also, there is a big separation has happened, and we can embed back here to figure out that if this is happening. Now because of this, what will be the problem which will be coming in the future? How much is the residual life of the system? So this can be reconstructed, rebuilt, that will turn out to be over, that will be the well established kind of thing. Now we are showing all three are in a kind of abrasive wear. Micro pilling is plowing is also abrasive wear, micro cutting is also abrasive wear, micro fracture or spalling also is abrasive wear. But this happens mostly into the brittle material, and this micro cutting and micro plowing happens in ductile materials. So this is a phenomena we can understand what we are getting and how do we relate it, how do we get come up with the right solution. Sometimes we divide or maybe say classify. We have a classification algorithms. We classify as adhesive wear or abrasive wear and all. But again, there is a lot of overlap. I'll just show you what is the overlap. We are saying here the key difference between the wear debris in adhesive wear and abrasive wear lies in size, shape, and hardness of the debris. So everything is a relative. Size itself is a relative, shape itself is a relative, hardness itself is relative. So what is the initial hardness? If the initial hardness is 30 HRC, actually whatever the debris will come from that. If the initial hardness is 50 HRC, hardness will be different. So mentioning that it is because of abrasion, addition is slightly difficult. So everything is relative in this manner. So here what has been mentioned from one of the paper, say adhesive wear produces smaller flakes and softer wear debris, while abrasive wear produces a larger, irregular shape and harder wear debris. So somehow I am not convinced with this. We say no. Adhesive wear also may occur from the harder debris also. However, we know that if the hardness increases, metal reactivity, molecule transfer comes down. So it should be on a softer side. But again, it's a relative. and then on the flags which are coming out. Now if the friction is on a smaller size or maybe lesser friction, the flags will be smaller. If the friction increased between the two surfaces, then again now it will be on a higher side. However, the justification comes that adhesive wear wherever occurs, because that there will be more plastic deformation, and when it is a plastic deformation, the material has to be softer. Now, if abrasive wear is coming from a ceramic material, and then they are using some sort of heterogeneous material, the quite possible the particle size may be smaller, medium, and larger also. All things are possible. And then, of course, a very irregular surface, I am not denying, but particle will be harder. Maybe if it is a really the heterogeneous phase, and which phase is coming out, whether it will be the harder or medium hardness of 40 HRC, will not be knowing well in advance. So I am using the word, this is a composite performance, not necessary it will be the harder. However, we are comparing with the adhesive wear, still I just can say it, but in absolute manner I can't. So everything will turn out to be relative. So this number has to be relative. So when we are saying softer, adhesive wear will be softer, where debris will be softer compared to the abrasive wear. Makes sense. Or abrasive wear debris will be harder compared to adhesive wear. Makes sense. Or adhesive wear debris will be smaller compared to abrasive wear. It makes sense. So these are the relative terms, and they are not absolute. So don't use this in absolute manner. Smaller particle means adhesive wear. No, smaller particle is compared with what? That makes more sense to us. Now, I'm just showing the two case study which people have done. I have picked up this in one of the research paper which was published in 2007, and this is offline monitoring. And then they in previous lecture I mentioned about the wear test. So they have done something like a ball on disc wear, and the ball has been shown, the disc has been shown, and they tested the two lubricant, trying to figure out which lubricant is giving good performance and which lubricant is giving a bad performance. So they have mentioned that they have soaked the lubricant so that lubricant remains for the there, and then they tested using, the first one is SA40, test 2 is something like an N32. So severe wear in N32 occurred after 72 hours, while in one case, first case is 168 hours. So from that point of view, I can say that N32 is bad, and as SAE40 is a good option. Of course, how they judge it, they try to figure out on they collected wear 20 wear particle from each experiment, and then they measure the surface roughness features, and then they have SA, skewness and kurtosis. Earlier in lecture 2 we use a word R, particularly when we are using the profilometer, and then we are going with a 2D measurement. When we are going with a 3D surface profilometer, then we will be using S. So all these values are from a 3D surface profilometer, it's not from 2D. And then they initially use a surface roughness mean value as a value as a 0.16, and it has gone 0.18 to 0.19. But again, this surface roughness is not giving very good overall comparison. Now in previous lecture or lecture 2 also I mentioned that skewness will be negative for the better lubricant. So if this comes on a positive, here it is a negative. So this is again not really giving results completely. Again, I mentioned that high kurtosis will be preferable. That's only the matching. In short, we say whenever we are doing a testing, we don't really require to take a judgment based on the one or two parameters. We need to take a parameters, many parameters, compare parameter, and then give justification why it is not really happening in this manner. Now, whatever the wear debris, we are able to see there is not much significant difference. If we go with variation is not that significant, then we need to really look at the volume flow on the volume which has been removed from a surface. So naturally they have taken decision based on the volume, and then they try to give a The surface roughness is a feature. That's why they say using the word prediction of the surface feature of your component based on the surface characterization of the wear. And then this test 1 is giving better performance compared to the test 2. However, the parameters S1 is not and S2 are not significantly different, and sorry, and they are saying the test 1 is better because the roughness in 119 is here, but as I mentioned, the skewness is on negative side, so test 2 should give a good results, but test 1 is giving good results. So from 2 point and the 0.18 it gives a good results, yes, justifiable. Kurtosis on a higher side, it is justifiable, but this value it is just under question why it has come down compared to this. If a skewness would have been on this side, on a more negative side, then would have been much better manner. However, when we change the lubricant, even the mechanism where they suck the lubricant, now if we bring the lubricant which remains as there, then maybe results may be different. So one, even changing the mechanism or lubrication mechanism can change the results. There's another example what we are saying, offline monitoring or prototype testing. Here the gearbox has been assembled in here, and then based on this gear performance has been checked. We are able to see and they have given complete conditions, hardness of the drive gear, driven gear has been mentioned, and then they have collected the wear debris, and then they are comparing this values also. So you can see here the valuation has been given. However, they also mentioned there is a sliding wear particularly occurring at the tooth surface on a during the disengagement time. That's what. However, they also have observed a pitting, which is very difficult to find the pitting in a lesser number of hours. So they have run it, and then for 70 hours at least we have done experiment, we don't find a 70 hours pitting happens. However, maybe they have done extensively much more load, and as I mentioned that when we go hard with this kind of analysis, we really require a complete situation, complete conditions. If we don't get a complete conditions, then we are not able to check it. So what is the output of this prototype testing? That where collection can be made, and then the judging that the sliding wear occurs because of the debris, and there's a pitting wear also occurs in this manner. However, in this case they have found very clearly there's no fatigue failure, because 70 hours running is very lesser time for fitting wear. However, they found a pitting here in the surface when they are showing it. So there is some sort of change what we are seeing, and then of course the sliding I understand, because if you keep a little lesser contact ratio, so in the misalignment the sliding will occur, but pitting is somewhat maybe not possible. What that also they have mentioned here, and they are saying that surface roughness has increased whenever there is a sliding wear. Naturally surface roughness will be deteriorated, and then they also have observed that it has not gone to the severe situation, because generally we use a word more than 100 micron when the severe wear condition, otherwise it is not severe condition. So they have not found a severe, that means they have started, and they maybe after 70 hours they have obtained this kind of a wear phenomena. Now there are some standards which we need to follow. As I mentioned in previous slides, we don't get all the information, but there is ASTM standard which indicate how do we get this information, and whenever there is a wear debris, how do we quantify. So we follow this standard, what we say ASTM F1877 standard, and of course this can be utilized for the biological purpose, but we are also utilizing for our purpose. Reason being, it has given a lot of information. They say that calculate aspect ratio, elongation, equivalent circle diameter, and roundness. But if we say roundness means it's not going to really damage the surface. If the particle is a round, then it will not be really very harmful. So as far as possible, particle should be round, and sometime we calculate equivalent diameter, so that has been given. So we will just explore the what formulas they have given. They have used a word roundness factor, it is a R, that's they are using two-dimensional thing. You can see here this is the area, and total area has been defined as a unit length, and then they are choosing the maximum dimension or diameter or whatever the maximum dimension. they are using this relation, naturally the maximum dimension will be equivalent, will be more than equivalent d max. So naturally, because of that, this r factor will be always lesser than 1, and it will be equal to 1 when only there is a sphere. So 4 shape have been shown. This is shape 1, shape 2, shape 3, shape 4. You can see here roundness factor r is here because this is a completely elongated one. So in this is the elongation is happening in this manner. So r factor is a 0.01, and this has a some sort of and the length and width both, that's why that is coming roughly 50%, 0.52. Again this figure is slightly this different degree is like a 1, what we have seen a 1 and 3 more or less same. Coming to the fourth, it is also like a 2 in the way, however here it is a shorter, so sometime it can give a lesser value, but here the one measurement it comes out to be 0.73. Now coming to the form factor, I believe particularly form factor is more useful compared to the roundness factor. Reason being, we are talking about the parameter. So I prefer the form factor compared to the roundness factor. Reason being that here we are choosing on the complete parameter, and parameter can really signifies, gives a complete dimension. So if there is a irregularities, parameter can easily capture that. That's very important. So now if you compare here, even the same dimension, you can see form factor 0.1 and r as a 0.1. There is no difference. Here r factor is 0.52, here form factor gives a slightly higher value 52. Here we were saying r factor 0.09, here form factor is a 0.14. Here find the r factor 0.73. Now this is gives a more realistic value to me, as I say that f factor gives a 0.68. So in my view, form factor will give better results compared to r value, and as I mentioned earlier, the r ranges from 0 to 1. 1 will be for the equal to the sphere. So these two parameters are important, and then d max, as I say, it's a maximum diameter they are mentioning, but it's a maximum dimension of a valve. So this is important to capture. And then other parameters, and one good thing about our MATLAB software is that they can calculate the boundary of any irregular shape also. You can see here algorithm, length can be dig out, and then maybe if we have a complete parameter, we can divide in number of particles, and between particle we can find out the length, and we can sum up those things. So finding this parameter will not that be difficult. If we capture image and we project in 2D, this parameter can be calculated. However, these two other three parameters are equivalent to circle diameter, aspect ratio and elongation. Again, elongation and aspect ratio are also quite similar to each other. Coming to the equivalent circle diameter, again we don't use extensively. Reason being that it is just to signify. Here equivalent circle diameter has been shown as a 1.38 micron, here 1.12 micron, 0.8 micron, 1.2 micron. So this, even though in all 5 cases shapes what we are considering are same, so this doesn't have a much meaning as such. However, if we want to really utilize for the equivalent dimension, some formula and mathematical model where you really require equivalent dimension, then equivalent dimension can be given over here. Coming to aspect ratio, we a kind of ellipse, we say maximum dimension and minimum dimension, that's why he has been shown. Only the difference is came the whatever the points, extreme points will be connected, the shortest distance between two, it's not along the line. However, in elongation we give complete along the line. If you see here, it moves along the line, so naturally elongation will be always higher compared to the aspect ratio. So what we are saying here, like in this case aspect ratio is 7.1, so it's a kind of cutting wear. Now if we go for elongation, because here we are not talking about the shortest distance between 2 points, here we are going along the line. You can see this is a, instead of 7.1 is 36.3. Coming to the aspect ratio, here in this case is a 1.4, but if you go with along the line, the length or maybe the maximum values, it will come out with 3.9. Again here 7.5, and here elongation 23.6. So I believe particularly elongation length will have a better value compared to aspect ratio. That's why we are writing here elongation E is a parameter like aspect ratio, but it particularly well suited for measuring the shape of significantly elongated particle. So in my view, we should use the elongation ratio and form factor as a two parameters for our purpose of wear debris analysis purpose. There is a one paper also which indicates on this computer image analysis of the wear debris. They try to quantify wear mode, wear mechanism and wear particle. Again, these are the somewhat related to each other. They are saying initially running in, it can be abrasion, it can be cutting, it can be addition. However, what we have studied, abrasion and addition, we have kept in one category. We are not kept in a separate category. And then they are mentioning the steady wear can be the abrasion, and wear out can be abrasion or cutting. Pitting can be related to only fatigue, and scuffing is only the addition. And of course, in running in initially, when the surface is we say that maybe the finish is low, it can be related to addition. So this is the one way to classify. And then however, these are the somewhat subjective again. They say particle size lesser than 15 micron, it can be categorized as a rubbing by micron size or rubbing particle. If a particle size is 20 to 50, it will be can be categorized as 20 to 50. As such, this is only experiential, it is not any basis as such. And particle size 20 to 50 laminar flow, and laminar again fatigue itself have been divided whether it will be spherical, it will be laminar, it will be fracture. And this fracture is basically for the brittle material, and laminar or spherical can be for ductile or can be for the and then the we say plastic material, polymer materials, that can be done. Also they have again given some dimension. We say that regular particle generally comes lesser than 50 micron. Now here this is a subjective, as I mentioned earlier one slide, we understood 20 micron, here it is a 50 micron. So it depends on the component. Instead of that, when we come up with a machine learning algorithm, we should give in a ratio, what is a percentage, and then it can be irregular also. If they are saying lesser than 50 regular and more than 50 micron is irregular. It can be elongated, we mentioned last time, a ball shape. Now here most of the time we believe the spherical particles which comes out of the particle is a natural phenomena, it will not cause a major problem. However, they have mentioned it is abnormal also. So here the size and particle those should come together. If particle size is coming 100 micron, spherical particle size is coming 100 micron, naturally it will be abnormal. If it is coming only 2 to 3 micron size, it is a normal particle, it's not an abnormal situation. So again, I'm using the word, this all of the subjective, we need to really quantify, or maybe when we account, we start developing models as per our knowledge. So this is what again here in this case they have separated wear out, pitting and scuffing. However, in our case we say everything is a wear out. In this case what we say wear rate initially is a running in, steady wear and then wear out. Now here they are dividing a wear out, pitting or scuffing. In our case it is only wear out, it's not a separate. So there are some differences in what we are teaching and what people have also published. So there is some difference, however we will go ahead with a much simpler case and then we can really model in appropriate manner. So we will be covering one case study, particularly the failure of the spur gear which we have tested in our lab, and this has been shown our gearbox setup. And this what we have done is a basically a bypass system where we are we're collecting oil sample regularly, and then we are passing through the metallic wear debris sensor, and then it is again after filtration it is sent back to the to the gearbox. So we are not extracting, we are continuously withdrawing and again resending back to the gearbox. Now here we have shown two setups. One is that we are operating at the 200 hours, second for the 100 minutes. And in 100 minutes we realize that when we do acceleration test, 100 minutes are sufficient, and we did a acceleration test using the mixing SCL. So we tested in two conditions. One, we mixed without HCl, lubricated, and another case is the lubricant was a mix with HCl that means we made a solution as acidic solution, so where it increases. This was done intentionally. We know that EP additives are more like slightly acidic, and then they make a corrosive layer and then increase the load carrying capacity of the lubricant, but it deteriorates faster. So this is what we have done. You can see here in this case Fe level has gone up to 100 from 28 and 29, and then when we collected the wear debris, we found that the huge change in the mass happening here almost with HCl. It is really increasing significantly. Now here what we are showing first Fe and ppm level in these two cases, with and without HCl, and then here we are showing a mass, then the wear mass again, that is the change in the mass particularly, and then here the again with a mass in the offline case. So there are two different things. One, we are saying when we are measuring using the wear debris analysis, so wear debris analysis, a mass with HCl is something like 73969, but without HCl it is a 66769. So there is a difference. When we are coming with offline, not rear debris, but where we are collecting oil and then we are filtering, and by doing a scientific action we are comparing, then we find with HCl variation is huge. So it is coming numbers something like 334 332400. There's a huge difference, while without HCl it is coming 138400. So there is a huge difference is coming. So many times when we are putting a sensor also, and if it is not able to the wear rate is very fast, then many times a particle they fall without getting notice of the sensor. So whenever we do this kind of online monitoring, we need to check both. One is that what sensor has given, and what oil he is really providing to us. So there are the two different things which we need to really compare and see it. Of course, when we did with HCl, and after that we use also nanoparticles, and then we again brought back to much lower level. So what we did in this case particularly, first we did acceleration test, and in accelerated test we increase the wear rate by 10 times, and then again we use some nanoparticle which will be kind of a nanotribology, and then again it has come down significantly. So this is a way we try to do the laboratory test and then wear debris analysis in a significant manner to understand, to learn about the wear systems, and then improve the system performance from that point of view. So this is my last slide. I say thank you for attention. Thank you.